Everyone, this is Kay. I'd like to present our work that uses imitation learning to teach a Chopsticks robot to solve fine manipulation tasks. So first you might wonder, why Chopsticks? We focus on Chopsticks as an example of simple tools for 4 reasons. First, designing a simple tool that is also versatile can be a challenging task, but Chopsticks are both. The shape of Chopsticks are easy to manufacture, model, and control. Humans have demonstrated versatile usage case with chopsticks, picking up big or small, hard or soft items. One widely dexterous human even used chopsticks to pick up cell phones. Second, applying a simple tools to a diverse set of tasks can be a challenging task. Manufacturers with special design shown on the left might put less burden on control, picking up different items at ease using similar policies. Simple manufacturers like chopsticks, as shown on the right, could pick up a diverse set of objects, but it would require a diverse set of strategies to handle different items. So the simplicity of design of simple tools transferred the difficulty to the algorithm design side. But who doesn't like some challenge? Studying general-purpose simple tools and overcoming challenges can still give us insights on developing sophisticated manipulation strategies, which may benefit both simple and complicated manipulation tools. Finally, humans have remarkable success using chopsticks. We hope to leverage the human expertise to teach our robot to achieve similar success. So today, we will teach the robot to learn from human demonstrations to use chopsticks and to pick up a small ball. So this is a fine manipulation task that requires precise movement. Even though we know that to pick up this ball, we just need to grasp at across the diameter of the ball, the grasping point have to be at exactly across the ball's diameter, allowing only some millimeter error. This task can be a suitably challenging testbed for general fine manipulation algorithms. Historically, one of the challenges faced in fine manipulation tasks is about building an accurate model of the robot. However, here we emphasize that we would like to solve this fine manipulation tasks with a general-purpose robot equipped with a simple tool. So we built our robot by assembling individual modulars which are not designed for high accuracy tasks, backlash, assemble errors compound along the robot arm, resulting in about 1 to 6 millimeter error at the manufacturer position. Like many other fine manipulation tasks, our model, we have one, but it's not accurate enough to allow us to solve this task using naive model-based control planning. However, humans could teleoperate this chopsticks robot to solve challenging tasks. In our previous work, we built a teleoperation interface and invited human experts to solve similar tasks of grasping. So the individuals in our experiments in just 3 trials have demonstrated significant improvements in success rate when picking up even the most challenging task, grasping this slippery glass ball. This interface proved to be a useful way for us to collect human demonstrations, as well as proving that it is possible to achieve this challenging fine manipulation task using a general-purpose setup without building an accurate model of the system. So all we need is a controller that's as good as our human experts. So we'd like to use model-free imitation learning to solve the task. We will evaluate our proposal on picking up 3 different items. Remember that our model has an error of 1 to 6 millimeter. So the distance between the estimated tip position and the actual tip position can be equal to the radius of this small ball that we want to pick up in our experiments. So on the left, we show our baseline. It's a naive behavior cloning agent, or BC. It struggles to pick up the small ball. On the right-hand side is our proposed agent, which achieved comparable performance to human experts. So we highlight that our baseline agent is suffering from covariance shift. Note that the robot chopsticks rotate as the robot approaches object. It's unseen in the expert demonstrations. So to illustrate, look at the right expert rollout, and in contrast to a learner rollout, which when the agent makes prediction error, it drifts to unseen states that the expert hasn't provided demonstration for. So the errors can compound, contributing to the covariance shift. To remedy, we propose to first transform the data to a different frame. So here, we would transform from this robot-centric frame to the object-centric frame. So after the transformation, we note that the data support is denser around the object. This is a critical region for a grasping task success. So when applying this on a real robot, we observed that the transformation improved the agent's success rate. However, failures can still happen. In both success and failure cases, the chopsticks can still be rotating as the agent moves. So we need a way to teach the agent how to react when it deviates from the demonstration. So to do that, we propose to use corrective labels for deviated states. So there are a lot of work on using or collecting corrective labels. So the most famous one, perhaps Dagger. It basically queries the expert for corrective labels on learner robots. However, we realize that this is actually pretty hard to apply to our task because even though I can teleoperate the robot to pick up something, I would not have any clue what to do when I am given any random state, like a slice of state, and I'm asked to provide the optimal action. It's almost impossible for me to give the optimal action label for any random state. Some other methods, like Dart, so they inject noise to the robot during teleoperation. So the robot now has a noisy controller. It will go to the place that the expert didn't intend it to go to. But the expert, since it's still in the teleoperation stage, it has to provide some action label. So this noisy controller will force the expert to provide corrective labels. However, because our task has requirement of high accuracy, we observed that experts become much more easily tired and had to spend like 50% more time for data collection on only 10 trajectories if we inject noise to our controller. So we don't want to burden our expert. Instead, we want to generate synthetic labels. So previous work like Data as Demonstrator or DAD, it basically used a model to roll out the learner policy, observe where the policy is deviating, and then trying to use model-based approach to come up with an action label that will bring the learner from the deviated state back onto some expert trajectories. However, generating this blue label here is not a trivial task. It is likely to require a model which we don't have an accurate enough model for. So we hope to generate synthetic corrective labels without burdening the expert or requiring a model. So we'll propose two methods. First, the noise injection. We propose to sample random states around the collected state and reuse the collected action as label. So this idea is not new. A lot of research have been injecting noise to input and reuse the output label. But for example, here, image recognition task. But note that the mapping is compressing a high-dimensional image to a low-dimensional label. So it's easy to see that even after we inject noise, the label would still hold and can serve as optimal label. But for our problem, we're learning a mapping from a low-dimensional space to another low-dimensional space. We actually cannot guarantee that for a randomly sampled state, the old action label can still work. Nevertheless, we propose to reuse action label. So the reasons are twofold. On one hand, even if the old action label may not be the optimal for the new state, it might still be informative. That is, if we assume Lipschitz smoothness in our policy function, we can generate a small enough noise and expect the old action label to be close to the optimal action label. So on the other hand, we observe that our task has a special structure. We're using a positional controller, and our state space contains n factor plus object position, and our action space also contains this n factor pose. So when we execute an action that is that comes from the demonstration, we're actually sending the robot to be closer to a pose that it has visited during demonstration. So if it can stay within the demonstration region, we can alleviate the distributional shift. So this will naturally help us stay on track if we can send more action from our demonstrations. So when we test this on our robot, we witnessed a great improvement in the agent success rate. Honestly, the authors ourselves are shocked about the amount of improvements here. If we look at the success rate change for the big ball, the ball 20 millimeter, we see that the success rate improved from 16% to 76%. And if we look at the video, we can see that the robot still rotates a tiny bit as it approaches the object. So finally, we propose to combine parametric methods like behavior cloning with non-parametric methods like KNN. The reason we want to involve non-parametric methods is because we believe that it will not generate any action that is out of distribution. What does it mean is because we have this key observation that non-parametric methods like KNN, they generate an output by interpolating the demonstrated outputs. So say that our robot's demonstration or compound around the right region of the desk. So even if our robot now moves to a completely opposite direction from demonstration, say like it goes to the left, the output from KNet, because it has to interpolate between the demonstrations, will direct the robot to go to the right. So it will bring the robot back to the demonstration area. And empirically, we also observe that the two methods have different causes of failure, which kind of confirm with our previous hypothesis. The behavior cloning agent, it can deviate from the collected demonstration, and that might cause it to fail the task. The KNN agent, by the way, I didn't pause the video here. The video is still playing. The KNN agent sometimes got stuck in the middle, and therefore it couldn't complete the task. But it does visit those states that are closer to expert demonstration. It stays close to what demonstrations look like. So we propose to combine the two methods. When the agent stays close to the demonstration area, we will invoke the behavior cloning agent. And when the agent deviates from the demonstration area, which, because KNN needs a distance function to work, we could write that distance function as our decision boundary. So the KNN distance function can tell us whether we deviate, and when we deviate, we will invoke the KNN. This allows the agent to have smooth trajectories that behavior cloning agent has, and also use KNN as a safety net that ensures that the agent gets back to the demonstration region after deviation. So finally, this simple ensemble model works the best. It achieved comparable performance to human experts. Here we show the video of our agent picking up the medium-sized ball. The success rate of the agent shown here is about 84%. To speed up the demonstration, the robot drops the ball after picking it up. It's actually intentional to drop it fast. So our proposal has a few limitations. It requires some domain knowledge about the task. If we want to transform the data to center around the critical region, we have to know where the critical regions are. And also, the way we generate corrective labels depends on this assumption we made, which is we're using positional controller, and therefore our state action space shares some structure. So it will probably not work for a torque-controlled robot, or at least not work as well. You might still be able to get some performance improvement to torque controller robot because of the Lipschitz assumption and smoothness. And we actually conducted some Mujoko experiment that we attached the figures in the paper. Nevertheless, even though the state and action space are task and tool dependent, we believe that the insights here can be generalizable to many other simple tools and tasks. So as long as you're planning to apply model-free imitation learning, the proposal here could perhaps help you come back the covariant shift problem in model-free imitation learning. And that concludes my talk. Thank you.